So thanks for tuning into this short video addressing the testing of fire resistance rated assemblies based on the requirements of the codes and standards which exist here in the US. Here at the National Fireproofing Contractors Association, otherwise known as NFCA, we regularly get comments about fireproofing products which are being marketed based on fire resistance testing, which does not comply with the requirements of the applicable codes and standards. The specific abuses we most commonly hear about are beams and columns tested on small scale testing and testing beams without the required load. So this video is intended to explain how beams and columns are required to be tested by the US-based standards and provide some suggestions on how to identify products which were not tested based on the requirements of the standards. So let's set the stage for our discussion by defining what we mean by full-scale testing and small-scale testing. These terms are not defined by the codes and standards, but do have widely agreed upon definitions in the industry. So when I say full-scale testing, I'm referring to testing of an assembly meeting the minimum size requirements of the two standards used to establish fire resistance ratings, ASTM E119 and UL 263. Small-scale testing is testing of an assembly which is smaller than that minimum size as required by the standard. For a number of reasons which we'll discuss shortly, testing assemblies which are smaller in size than required by the two standards is a less critical evaluation. Similarly, the standards also require beams, floor ceilings, and roof ceilings to be loaded during the fire test. Generally, assemblies are loaded to their maximum design capacity during the testing, although there is an allowance in the standard to test something other than a maximum design capacity, as long as the resulting report and listings clearly state the allowable load that was tested. Once again, for a number of reasons which we'll discuss shortly, testing assemblies at something other than the maximum allowable load is a less critical evaluation. As we know, fire resistance rated construction is intended to contain a fire to the room or floor of origin and to maintain the structural integrity of the assembly. This is done through the use of building materials and construction techniques which are designed to resist the long-term impact of fire. So let's talk for a minute about the code requirements for fire resistance rated construction. I have images of both the NFPA 101 Life Safety Code and the International Building Code on the screen. Although I'll be paraphrasing from the requirements of the International Building Code, conceptually, the requirements of the Life Safety Code are very similar to that of the IBC. Assuming you already know the required fire resistance rating, Chapter 7 of the IBC provides further details on how those ratings are determined. I call this the nuts and bolts chapter relating to fire resistor construction. Some of the key points include the following. First, fire resistance ratings shall be determined in accordance with Section 703.2.1 or 703.2.2 without the use of automatic sprinklers or any other fire suppression system being incorporated, or in accordance with Section 703.2.3. So the first of those methods references tested assemblies. It simply states fire resistance ratings shall be determined in accordance with ASTM E119 or UL 263. So the design professional simply provides a copy of the report showing the assembly was tested to one of those two standards, and that is the method of showing compliance. Is that practical? Probably not. So fortunately, the code gives some additional methods. The second method is referred to as the analytical method. It states that methods for determining fire resistance shall be based on the fire exposure and acceptance criteria of ASTM E119 or UL 263. Required fire resistance is permitted to be established based on any of the following. Then there's 5 practical methods by which one determines fire resistance. Designs documented from approved sources. An example of that would be the Gypsum Association Fire Resistance Design Manual. Gives the construction and ratings for many variations of gypsum board construction. Beyond that, we have prescriptive requirements from Section 721 of the IBC or calculated fire resistance from Section 722 of the IBC. Neither of those are widely used in our industry, but certainly in other industries they are. And then we have the engineering analysis based on ASTM E119 or UL 263. Most people would refer to that as engineering judgments. And then last but not least, we have fire resistance designs certified by an approved agency. That's where the product directories from the various test labs come into play. You know, the UL online directory, Intertech online directory, or FM approval guide all gives fire resistance designs. So those are your 5 practical methods. And then moving on, we have that third method of showing compliance with the codes, and that's through the use of Section 104.11. Section 104.11 is a section of the code that's been around for many decades. It relates to the use of alternate materials and methods. Gives the allowance that the design professional can provide information other than the prescriptive requirements of the code to justify their achieving the required level of safety demanded by the code. And this section doesn't have a lot of relevancy for the fire resistance world, but it does exist. You've probably heard Bill and McHugh and I talk recent webinars about a change that has taken place in Section 104.11 for the 2024 International Building Code. And basically the phrase fire resistance has been replaced by the phrase fire safety in Section 104.11. And the concept behind that change was the proponents wanted to allude to and make reference to fire safety in a broader sense than just limiting it to fire resistance. So now that phrase takes into account all aspects of fire protection, needs to be considered when using 104.11. So let's look at how fire resistance ratings are established. And ultimately, this will demonstrate why small-scale testing and testing of non-loaded or unloaded assemblies has no place in the fire resistance world. So ultimately, the ability of a construction technique to perform its function as a fire barrier is evaluated in accordance with the standard fire test of building construction and materials, ASTM E119. The same test method is also known as UL 263 and NFPA 251. The reality of it is that those 3 test methods all describe the same equipment, same test procedure, and the same conditions of acceptance. So they can be considered interchangeable. And I've noted here that NFPA 251 has been withdrawn, but the reason I maintain it on this slide is the fact that CMS requires healthcare facilities to comply with the 2012 edition of the Life Safety Code. That edition of the Life Safety Code still references NFPA 251. So until that edition of the code is no longer in use, I keep this reference to 251 on the slides, but just keep it in mind that those 3 standards are all one and the same. So for testing purposes, the standard divides a building into individual components: columns, beams, floor ceilings or roof ceilings, and wall assemblies. And the standard then contains procedures for evaluating each of those types of assemblies. All fire resistance tests are conducted using a standard time temperature curve. And this temperature curve is the assumed fire exposure that you might have in an actual commercial building fire. So the temperature within that furnace would reach 1,000 degrees Fahrenheit in 5 minutes, 1,700 degrees Fahrenheit in 1 hour, and 2,000 degrees Fahrenheit at 4 hours. So now let's look at the requirements for beams and try to clearly demonstrate why small-scale testing in non-loaded assemblies has no place in this testing world. So the standard defines the minimum sample size as 12 foot. The standard also requires the assemblies to be loaded during the fire test. Now, the default position is that those assemblies be loaded to their maximum design capacity during the fire testing, but there is an allowance in the standard which does allow assemblies to be tested at a reduced design load as long as the resulting report and listings clearly specify the allowable load on that assembly. So let's look at the construction and testing of a typical beam assembly. So this photo, or this next series of photos, represents beams which are used to support a steel deck concrete floor assembly. So we're looking at some photos taken at UL's Northbrook, Illinois testing facility. So UL uses concrete and masonry test frames for the construction and testing of their assemblies. So in this case, we've got this concrete masonry test frame around the perimeter of the assembly. We've got 4 beams spanning the short dimension of the furnace. And so next step of the construction process would be to install the steel deck on top of those beams. And then concrete is poured on top of the beam, leveled smooth as would be done in the field. And then the assembly is allowed to condition. Concrete typically will take 4 to 6 months to condition or cure prior to the fire exposure test. Once the concrete has cured, the assembly is turned over to the sponsor of the test, who will then apply whatever protection material that they're testing to the underside of that assembly. And prior to the application of that material, the testing laboratory will install thermocouples on the steel or in the steel so that they can measure the temperature during the fire exposure test. So this photo gives you a relative feel for the size of the furnace. The furnace is 14 foot by 17 foot in size by roughly 6 feet deep. So Andy is standing in the furnace, so you get a relative idea of the size of that furnace. So then the test assembly is placed on top of the furnace. The test assembly ultimately rests on the furnace, which is in the basement of the testing laboratory. So we're on the first floor of the laboratory, looking at the top side of the test assembly. This racking system on top of the assembly is what's used to apply the load to the assembly during the fire exposure test. So the assembly is loaded, furnace fire is ignited, follows the standard time temperature curve. And during that test, the lab is making visual observations on the performance of the assembly, along with looking at the conditions of acceptance of the standard. And the conditions of acceptance of the standard would suggest the assembly needs to support the load, and it needs to limit the temperature of the structural steel of the beams to an average of 1100 degrees Fahrenheit and to individual point temperature limitation of 1300 degrees Fahrenheit. So when either one of those criteria is met, that would be the fire resistance rating of that assembly. So now let's look at why it's so important that these assemblies be tested on a loaded full-scale basis. So a loaded assembly allows for a realistic beam deflection. Likewise, the testing of a full-scale assembly also allows for that realistic beam deflection, but it also eliminates the edge effects at the end of the beams. And long ago, when the standards were written, the authors recognized that the tests needed to be conducted on assemblies which replicated construction in the field. We needed samples that were large enough to allow this realistic beam deflection, and we also needed samples that were large enough so we could eliminate the ends of the beam from the evaluation and just look at the center section of that beam and have a sufficient length to get a realistic temperature measurement on those beams. So this photo is taken through one of the viewports on the furnace, looking into the furnace. So what we're seeing is this beam assembly has a very significant amount of downward deflection in the latter stages of the test. That downward deflection could be in the order of magnitude of about maybe 9, 10, 11 inches. So that downward deflection then puts the bottom flange of the beam in tension, and the bottom flange expands, ultimately resulting in cracks and voids developing in the protection material, and sometimes even delamination of the protection material. If we didn't have that deflection, realistically, we'd have a much less critical evaluation because those cracks and potential delamination of the material wouldn't happen. So that's the importance of testing these assemblies on a full-scale basis and also testing these assemblies with a load applied. It results in that deflection. The other thing to consider again is the edge effects of the furnace. The beams span the test frame, and that test frame is a very heavy concrete steel frame. So the frame acts as a heat sink for the beam at the ends of that beam. So it absorbs some of the heat that's seen by the beam. So ultimately, the ends of the beam will see less temperature increase than the center section of the beam. So these thermocouple locations, these sections AA, BB, CC, DD, etc., are a series of thermocouples applied around the perimeter of the beam at those various locations. So sections AA and BB are roughly 3 foot from the ends of the beam or the walls of the furnace. So that puts them in a section of the furnace where they're going to see a representative heat load as a result of the fire exposure, and give a representative temperature that we would expect on those beams in an actual fire. So if we were evaluating these assemblies based on a small scale, we wouldn't have enough length of beam to get out of that edge effect distance at each end of the beam. So we wouldn't be able to realistically develop accurate temperatures of what those beams would see in an actual fire condition. So that's again the other reason for testing on a full-scale basis. So now let's turn our attention to columns, and most of what I said relating to beams would also apply here. Standard does have a minimum size of column, that being 9 foot in length, and the standard defines 2 test procedures. The first is to test the beams unloaded, with the conditions of acceptance being based on the temperature of the steel. The second is to test those beams in the loaded condition with the conditions of acceptance based on the loading or being able to maintain the load during the fire exposure test. Now, here in North America, most often, and more realistically all the time, the testing is based on unloaded test specimens. There are no laboratories here in North America that have the capabilities of loading columns during that fire exposure test. So again, I've got a series of slides which show the construction of a typical column assembly. So we see in this case a square tube column being protected. So we've got a concrete cap at the top of the assembly. We've got a base legs welded onto the bottom of the column to keep it upright during the construction and testing process. The laboratory staff applies thermocouples to the column prior to the test. And now the test sponsor comes in and applies the protection material to that beam. After that protection material is cured, it's placed into the furnace. This is UL's column furnace in Northbrook, Illinois. And the thing to notice here is that the base of the column is buried in a bed of sand. So the last few inches at the lower end of that sample is not directly exposed to fire. So then the fourth wall of that furnace is slid closed, and then the furnace fire is ignited. And ultimately, during that test, what we're simply looking for is when the temperature when the average temperature of all the thermocouples reaches 1,000 degrees Fahrenheit, or where any individual thermocouple reaches a temperature of 1,200 Fahrenheit, that would be the fire resistance rating. Now, if the assembly was tested load bearing, the criteria there would be that it would need to continue to carry that load during the rating period, or in other words, when it reached a point of structural collapse, that would be the fire resistance rating of that assembly. And I mentioned before, there are no labs that can conduct load-bearing column tests here in North America. So, one might ask, well, is testing a non-loaded bearing assembly representative of an actual column in the field? Well, the realities of it is yes, it is. And the reason I say that is, there are furnaces both in Asia and in Europe that can test load-bearing columns. And the correlating fire tests that have been done between the temperature-based criteria and the load carrying capacity criteria, has been compared over the years by a number of different manufacturers, a number of different materials, and the conclusion of that testing has shown that the US-based, temperature-based criteria is in fact more critical than the load-based criteria that's contained in the standard. So we can confidently say that yes, we are evaluating these columns in a realistic manner that in fact represents a more critical evaluation as compared to subjecting them to testing under load conditions. So with columns, we have maybe a slightly different reason for testing full scale, but it's the same concept. We need to test a column on a full scale assembly in order to eliminate those edge effects I talked about before. In this case, it would be at the top and the bottom of the column. So once again, I've got the, I call it the thermocouple layout that's installed on the column prior to the fire exposure testing. That's ultimately used to measure the temperature of the steel for compliance with that 1000 degrees, 1200 degree Fahrenheit criteria. So you notice the thermocouples at elevations AA and DD are located 2 foot from the top and the bottom of the column. Again, eliminating or taking it out of that edge effect zone. So we've got 4 sections of temperature measurements that are made in the middle section of that column, so we get accurate temperature readings. So if we had a small scale sample, we wouldn't have that section in the center that reaches representative temperature. So once again, it's critical that we do test these assemblies on a full scale basis to eliminate that edge effect and to be able to achieve representative temperatures on that column during the fire exposure test. So this is another way of looking at that same concept of the edge effects. Remember I mentioned the sand base that's used in the column furnace? So the last 4 or 5 inches or lower 4 or 5 inches of this test sample was buried in that base or bed of sand. So it didn't see much heat. So if we look at the very bottom, we see the intumescent fire resistant material has really seen very little heat, has not expanded at all. And as such, then the steel underneath it, likewise, is very cool. So as we move up in elevation, the column comes out of that bed of sand and sees a reasonable amount of heat. So this lower section of the column would represent a heat sink, would lower the temperature immediately above it on the steel. So we need to maintain sufficient separation from the base of that column to the first level of thermocouples so we eliminate that edge effect. So I won't get too involved in floor ceilings or roof ceilings. It's more or less the same as what we've talked about before. Once again, there is a minimum sample size requirement. In this case, it involves both a minimum dimension of 12 foot along with a minimum area of the assembly of 180 square foot. And once again, these assemblies are required to be loaded. The default position is they're loaded to their maximum design capacity for the construction being tested, or they can be tested at some reduced design load as long as the resulting report and listings clearly specify that allowable load. And once again, the concept of loading that assembly allows for realistic deflection of both the beam and also the general floor or roof area, the floor roof deck, in other words. And likewise, the concept of the use of full-scale assembly allows again for that realistic deflection of the beam, floor or roof, and also eliminates the edge effect at the perimeter of that assembly. So once again, it's critical that we test these assemblies fully, I shouldn't say fully loaded, but loaded as required by the standard in a full-scale basis. So here's the take home, I guess, in terms of this program. And how do you determine if an assembly was tested based on the codes and standards? Well, sometimes it's not necessarily so easy. I'll be the first to admit that. But the first thing you want to do is look at the listing. What listing documentation exists for that construction that you're being asked to look at or to use? And if you're looking at a UL listing, or for that matter, Intertech FM listing, the laboratories maintain what UL calls guide information, which talks about how these assemblies are tested. So for each individual design, you can click on a link on the upper left of that design, takes you to the guide. the guide will clearly specify that these assemblies were tested to ASTM E119 UL263, which then implies full-scale testing, fully loaded samples. Another method of making that determination is look at the manufacturer's cut sheets. Does it reference phrases like small scale or reduced size, limited size, words like that? If so, then that's not an assembly that meets the requirements of ASTM E119 or, for that matter, the codes. Likewise, does it state something like it was essentially tested in accordance with or tested to a modified E119 test or based upon the concepts of ASTM E119? Things like that. If you see any phrases like that, again, those aren't assemblies that meet the requirements of the code or meet the requirements of the standard. So also, if you're looking at a cut sheet or something that references a lab you might not be familiar with, look at the website of that lab and determine if they even have full-scale furnaces. If they don't have a full-scale furnace, then it's pretty obvious that that assembly wasn't tested based on the requirements of ASTM E119 or UL263. And I suppose you could also look at the website from the manufacturer, see what information they have in terms of what testing they have conducted and where they've conducted it. But bottom line is, if you have any doubt on whether it was tested full scale or small scale, ask for a copy of the test report. The test report will very clearly specify the size of the sample, exactly how it was tested, whether it was loaded or not. That's the final proof. If there's ever any doubt, ask for that test report. So hopefully you found these tips to be helpful. Hopefully you found the program to be helpful. So thanks for listening in on it. If you do have any questions or comments, please feel free to reach out to us at National Fireproofing Contractors Association. The phone number is shown here along with an email address, info@nfca-online.org. Send us an email. We'll be happy to answer whatever questions you might have. Likewise, refer to the NFCA website. There's a tremendous number of resources available on that website to help you meet your fireproofing needs. So again, thanks for listening. Thanks for participating today.